Look at the agenda. Just from go to the IETF agenda. No, from the IETF agenda.
Used to be here.
From the whole, not data tracker, this one, this agenda.
How did you get there?
IETF.org.
Yeah, figured it.
The agenda. RTGWG. Full. Okay, get started.
Yep, start. People settle really slow.
Good morning, San Francisco. Probably we need to yell so you wake up, right? Welcome to Routing Working Group, session number 1 in San Francisco. And let's kick it off.
So maybe people in the back can close the door, please.
Martin, can you please close the door? Anyone at the door? Could you please close the doors? Thanks, Kate. Oh, it takes 2 ADs to close the doors. That's cool. One former, yes. So, welcome, Ingen and myself, welcoming you to San Francisco. And let's go through our usual chair chat. So not well, you should be familiar with everything in here by now. So let's go further. IPR disclosure, Routing Working Group runs IPR disclosures twice when we adopt the document, when we go through working group last call, unless each and every author and contributor has responded, document is not progressing. Please pay attention. We've also said that ISG is going to strictly enforce 5 authors rule. Please make sure you are not 6, not 8, but 5 at most. So progress, the VRRP 5798B is in working group last call. It's in progress. Good document. Thanks to authors for working on it. Please comment if you have disagreements. I mean, it's a very straightforward document. AC?
Yeah, I'm the AC Lindum Levin. I'm the primary editor on this. I am, it's a matter of bandwidth. I got a bunch of stuff to do in LSVR, but I am going to do the Yang model as well. Now I'm kind of watching this discussion in NetMod on non-backward compatible changes. I'm hoping I can change it without, because when you're doing an inclusive language, if you leave the old nodes with the deprecated, it kind of defeats the purpose. I guess at some point they could be removed. So I'm hoping that for these read-only nodes, they're going to let me change them from master to act, you know, the terminology. So, but that's the next on the list, and I'm also going to do that here, that Yang model, because the original, I was offered the original Yang model, and it was done here.
Do you want to poll NetMod here? What's the plan of options? Or are you just going to do it?
The discussion is going on the list on the net right now about how non-backward compatible changes are going to be handled with semantic versioning.
Okay, we'll track it. Next slide, please. So we've got a whole number of existing working group documents which we would like to progress, and we definitely need some people to pay more attention here, especially on peak draft. Oh, I see someone is walking in.
That is all. Very good.
Guys, please do pay attention. We would really like, after 4 years, these documents to progress. It has no reason to sit where it is now. It's ready. So TILFA, the review is in progress. We hope to start working group last call probably a few weeks after IETF. Net cloud problem statement. We did do early review. We are still somewhat unhappy about quality of the document and language, so we'll continue working on it with authors. For services secrets protection, we initiated the early review. We'll update you Friday what's going on. And QS model, we believe it's pretty much ready for working group last call. Authors working with us on getting it ready. We'll update you Friday. So agenda for today, obviously you're going to see everything, so no reason to read it again. Agenda for Friday, same applies here. And let's start. We've got busy agenda today, so. Please don't forget to scan the chat code, and we would like to keep getting larger rooms. So please make sure you are here.
So for people on site, please make sure you scan the QR code over there. And when you want to ask a question, you can put yourself in the virtual queue.
Okay. Okay. Good morning, everyone. I will provide a short updates on the signaling in network computing operations. Next slide, please. So since previous meeting in Yokohama, we did some updates. So roughly this is the status. The major part is we added the control plane consideration based on the feedback we received from IETF117. And we also have new authors from Huawei and from China Mobile. Next, please. So here you have an overview about what has been updated. In the introduction parts, we clarify the difference between CATS and SYNC, thanks to the comments from Adrian. And we also add a very brief comparison from the shop as switch MML or net reduce. And then in the document itself, we specify how a SYNC switch or router can examine the SYNC header. Most probably, we will leverage the existing encapsulation protocol capability. Otherwise, we do a DPI. We also specify in the batch computing mode that we need to define a topology rather than just do as individual computing mode. The major part actually comes with a control plane requirements. Instead of requirements, so we expand it to a control plane consideration with a lot of thoughts on how should we design a control plane. But yet, this document we aim to produce the design of the protocol and the data plane itself. So the control plane we were thinking to put into a separate document. That's why in this document we just put some considerations, but extensive considerations. And besides, we also removed the computer capability operation abstractions based on the comments we received from the previous meeting. And overall, we did text refinement. Next, please. So this is actually a kind of a recap of different use cases and the very concrete use cases like a net reduce, net distributor lock, and net sequencer. Those are the use cases or applications we have been implemented. So in our case, we mainly implement in the context of HPC. So the aim of this draft is design a explicit and general mechanism to signal the switch in the network and let them know how to process those packets. Next, please. So those are a bit into detail what we have changed in the text. In the introduction, as I said, so we clarified the difference between CATS and think. CATS is more for the service instance selection, while what we do in the think is more like a light state calculation performed in the network. We also specify that the sync switch or router in the network is able to examine the sync header based on the encapsulation protocols if they have the explicit field like next protocol. If not, then the DPI probably will be used to identify location of the sync header. A brief comparison between switch ML, sharp, and NetReduce has been done. Mainly, we find those protocols are mostly focused on the aggregation operation, while we want to define a more generic data calculation mechanisms. So last but the batch modes computing is what I just mentioned, that we want to enrich with not only the operation, but also the topology creation. Next, please. So here about the control plane consideration. So the control plane need to consider how could we create such a topology? How do we delete that, right? So when you receive some requests from the host, you should be able to calculate that and to see whether based on existing resources, you are able to perform this operation. And if so, how do you define this topology? Once you did your calculation, you need to actually configure the network accordingly. And last but not least, when this has been done, then it has to be deleted. So all this should happen, according to us, in the control plane itself. The control plane should also have the capability of doing the resource reservation, not only reserve the network resources, but also the computing resources. It will also do the performance monitoring, because if something failed, as I mentioned, there should have some mechanism of the service protection. So it should protect the service in case the computation failed, or it should protect the service in case the network failed. Next, please. So based on that, so we list a few like control plane requirements, which indicate that the control plane, for instance, should be able to have a kind of a user network interface to exchange compute requirements and execution status with the application. It should be able to monitoring all the resources and how much they are still there. It should be able to create dynamically create, modify, or delete the network topology, and it should also provide some kind of a failover mechanism. Next, please. And then small updates on the deployment consideration, mainly to update the MPLS part. Next, please. So in the previous documents, we haven't explicitly mentioned how in MPLS tunneling, how do we actually look for the thing header. And afterwards, actually, we look at the protocol itself. We find that there's a field called the next hop label forwarding entry defined in MPLS, which could be well used for the purpose of defining the next hop in the next protocol, which can be well used to indicate where the sync header is. So in case of the MPLS tunneling, we can do that properly. So that is the updates for the for the deployment consideration draft. Next, please. Yeah, so that's all about it. It's a very brief and a short update. If you have any comments.
Adrian?
Hi, Adrian Farrell with my CATS co-chair hat on and my Alto sort of rubber gloves on. You're talking about building a sync topology where essentially you're finding out what the sync nodes are capable of to build a topology. Is that a dynamic topology? In other words, can the sync nodes be updating according to maybe their queue lengths and things like that?
Well, I would say it would be a dynamic one because, for instance, if the network is empty, the node can do some simple calculation. But once they already have some workload there, then they also need to report their workload basically. So you cannot really add on top of a 100% workload there. Yeah.
Okay, then what I would be interested in doing is trying to get a common view of compute metrics, the compute capabilities and load metrics and things across this work, CATS and Alto. It's early in the week, but at the Alto meeting, when it comes later, I'm going to be suggesting that CATS and Alto need to get together and have an interim to discuss compute metrics. It may be that they turn out to be completely separate things. I will try to remember to flag to you when that interim is coming, because it sounds like we should get everybody in the same room.
Okay, thank you. I think
a couple of comments as a working group member. Number one, please take a look at technologies that have been developed here in the last couple of years, because resiliency is very important. There's a number of technologies to protect tree structures. Please make sure you are taking into consideration how to deal in case of node failure that is on the tree or is already doing some computation. Number two, this is really targeting data centers. MPLS and data center, as much as you allow it, is not deployed. So potentially you might look into something like Genève. I mean, I wouldn't look into VIX, that would be a choice. Genève would be for sure a much more interesting constellation for data centers. So UDP IP, not MPLS.
Yeah, okay, thank you. So definitely we will consider the resilience issue. As we mentioned, probably we will consider that in the control plane parts could be probably come from a separate draft. For the second question, I think it's very good. You mentioned that because we separate from main spec from the deployment. So in the deployment, we only give 2 examples. We can well add Geneva as the third example because it's mostly used for.
It would be much more realistic use case.
Yeah. Okay. We will do that.
Thank you so much.
Yeah. Thank you.
And while maybe this value of this work wasn't very obvious a year ago, probably now with everything that's going on and again, size of models, networks, it could save up to half of the bandwidth if done properly. So it's going to be a very important point. Thank you. Adrian, so we are going to coordinate on interim, potentially do it between routing and CATS, right? Thank you.
Can you hear me?
I didn't say anything. Anyone in queue?
Can you hear me?
Yes, we can hear you. I pass the slides control to you.
Okay, let's begin. Hello, everyone. I'm glad to be here to present this draft. Next page, please. Before diving into the Dragonfly problem statement, we didn't have enough time to present at the IEDC slide meeting. The chair suggested provide a brief overview during this session. Here are 2 slides that outline the key points of discussion in IEDC. The focus is on potential direction for AI data center network and the challenge they currently face. Next page, please.
You have control of the slides.
Okay. 好。Currently, AI data center networks are facing challenges such as limited performance of GPU cluster, uneven network traffic, and low polarization in congestion control. Innovation are needed from multiple sectors to address this challenge, and we can explore new network topologies. Currently, data centers still rely on factory architecture. In the future, we can reach such new topology themes, such as Dragonfly or Dragonfly Plus, to overcome the limitation of the current architecture. Secondly, we can explore the use of new protocol stacks from the physical layer to the application layer. We need to focus on low latency, load balancing, simple protocol, and better RDMA to achieve a high-performance data center network. This approach aims to improve the overall performance of the network. In terms of new topologies, Dragonfly is one such management topology. In our group, we already have relevant drafts discussing Dragonfly. The drafts will be the focus of our upcoming presentation. In terms of the protocol stack, we have conducted research on SRv6 for DCN and MSR6 for AI multicast offloading. The relevant drafts has been attached for your reference. Additionally, we have also made innovation in the physical layer and the data layer with a new architecture called GSE. The GSE architecture includes features such as packet spraying based on packet container and lower latency FEC. Detailed information about GSE can be found in the GSE white paper posted by CMCC. You can scan the QR code provided to download the white paper. All right, we will indeed research on this topic gradually at IETF in the future. If you are interested in this, we can communicate by email. Certainly, let's go back to discussing the Dragonfly topology. Today, Dragonfly, characterized by its small network diameter and low cost, has been widely adopted in HPC network. However, Dragonfly architecture still has many shortcomings. This draft addressed the current status of Dragonfly technology, describes the exciting issues in Dragonfly network, and outlines the future requirements. In topology of Dragonfly, there were several key characteristics. The first characteristic is the full connectivity between groups, meaning that any two groups can continue directly. The second is that within each group, any topology can be employed, such as the commonly used factory architecture. The third focuses on reducing the number of links and the network diameter to minimize network cost. Lastly, the Dragonfly network relies on adaptive routing to efficient network operation. The Dragonfly topology consists of switch layers, group layers, and system layers. The switch layers consist of a switch and several ports, with some ports connected to the switch and other connected to other groups. The group layer consists of multiple switches that are fully interconnected. The system layer consists of multiple group layers with full interconnection between groups. So these characteristics and the structure or topology make Dragonfly particularly suitable for large-scale computing and data center environments. However, it also comes with certain issues and challenges, which will be discussed in detail in the following discussion. Certainly, there are four common known routing algorithms in Dragonfly topology. The first routing algorithm is MR, determines the shortest path between source and destination nodes using routing protocols such as EASIS or OSPF. This method, also widely used, suffered from the problem of load imbalance. The second routing algorithm is NMR. Currently lacks a standardized method. Progress in this area has been made through manual configuration to guide route forwarding and load balance. The third routing algorithm is AR. It dynamically switches between the shortest and non-shortest paths based on observers' congestion levels and other relevant information. To avoid load-back, a solution is achieved through VPN. As shown in the diagram on the right, traffic is routed through the 1-3 path. However, if congestion is detected on the local link, the adaptive routing algorithm switches to alternative paths like 143 or other non-shortest paths. Similarly, as shown in the lower diagram, if congress is detected on the global link, the algorithm switches to alternative paths. So the advantage of AR is that it doesn't require no manual intervention, dynamically adjusting routes to prevent congestion. The fourth routing algorithm is VLB. It calculates the product of link length and the congestion level along the path to determine which path to take. However, there's currently no standardized method for obtaining congestion level information, which poses a challenge in implementing this algorithm uniformly. Below are the current issues with the routing machine in Dragonfly topology. In regards to NMR, currently there are two approaches to guide traffic forwarding in NMR. The first approach involves the manual adjusting weights and costs to select the path for traffic forwarding. The second approach is using BGP routing policies and attributes to select the path for forwarding. However, they require additional management and configuration, leading to complexity in network management. They may also introduce longer delays and occur link bandwidths. As a result, there's currently no practical method to dynamically adjust the load on paths and achieve effective load balance. Due to the need for manual configuration of minimal path routing, AI is not flexible enough, especially when multiple congestion ports occur. This can lead to packet loss and an inability to forward traffic. As shown in the diagram on the right, when congestion occurs on the link between the source and the destination node, the traffic will be routed through path 1, 4. If congestion occurs between nodes 5 and 7, traffic from node 4 will be rerouted through path 5, 6, 8, 7. However, when congestion occurs between nodes 7 and 12, traffic flow is disrupted. As a result, the situation is similar to what was described earlier, where there is currently no dynamic load balancing method available to address these issues. In addition, it's important to have congestion awareness when dealing with congested links. ARN is the information used in AR routing, but currently there is no standardized definition for it. ARN can include information such as current dips, bandwidth utilization, device load, and performance metrics. However, there are still several issues with ARN, such as time-sensitive scalability challenge, security. Addressing these issues in ARN is essential to ensure accurate and timely congestion awareness and effective congestion control in the network. Based on the above analysis, I will summarize the two major issues faced by the Dragonfly network. The first issue is that the current system relies on manual control of traffic forwarding paths, leading to a lack of dynamic load balancing. The second issue is that the existing network architecture lacks a standardized definition of network congestion and a mechanism for reroute congestion notification, made it difficult to exchange congestion information in a timely manner. Based on the above issues, we have identified 5 requirements for this topology. We need to consider the requirements in terms of low latency, load balancing, scalability, adaptability, and reliability. Okay, that's all. Welcome any suggestion and feedback from everyone. Please share your thoughts and suggestions. Thank you.
Hi, Andrew Alston here from Liquid. I've got 2 questions about this. Firstly, I'd like to understand, have you looked at the Rift materials and what does this do that is not solved by Rift? So what are the differences? You know, what is the current case outside of Rift? Would be the first question. And the second question is, I noticed in your list of references to kind of related work, etc., you made reference to a draft in Beer. Now, I'm a little confused at this point because I'm not sure where work is continuing in Beer on this stuff or where people are still trying to take it out of Beer. So I'd like to know, since you referenced the work, are you planning on continuing with some of that work in Beer in addition to this? Because it does influence where we see this going with regards to the related work. Thanks.
Okay. So question 1. I think as I understand.
We should. This is with company. I'm also the author draft. I would like to answer this question. Can you do that?
We cannot hear you. Please talk louder and slower.
Yeah. So, could you hear me now?
Yeah, reasonably. Try to talk a bit slower.
Okay. So, for the first question, compared to Rift, the Dragonfly maybe can be used some specific application scenario. This draft we just give some analysis. We would like to provide some problem statement and the preliminary gap analysis. We hope the members in RTGWG who can work together on that. We believe there are some potential use case in the future with the Dragonfly. We don't intend to use Dragonfly to replace the Rift solution. And for the second question, as you mentioned about the multicast solution, I think that page we just prepared for the side meeting. I think yesterday. In that page, we list several possible way to improve the AI data center network. The new broadcast or the new multicast solution is one of them. As of the while we should do that, I think that is an open question. Here we just raise a problem here because we did not present it that in the side meeting due to the time limit. So next step, if possible, we hope AD and Charles can guide us to do something, maybe in some other working group, or maybe the new working group. Thank you.
Andrew, are you satisfied with the answer?
Yeah, I'll actually apply to the list, I think.
Yeah.
There's a lot to respond to there.
So probably we should move on, right? Let's move on. Dima? Please make it a point to finish on time and throw all your slides, right? Because otherwise we'll just cut you out. Make it a point.
Yeah, because there are a lot of slides, but I can skip half of them. And previous talk conveniently described some problems, so I really can go faster. Okay, so I'm Dmitry Afanasyev, and I'm going to talk about a particular solution for routing in Dragonfly topology, and well, particular flavor of it actually, Dragonfly Plus. We'll briefly describe problem, why we want to deal with such kind of things, and some solutions, and also we'll talk a little bit about some missing pieces, except for adaptive routing, for example. Next slide, please. So very briefly, why we are interested in new topology? When we have CLO and multi-stage CLO scales well and works well enough, problem is that we want to do several things. First, we want to scale better and cheaper, so be able to build larger network from the same number of switches and links. And in modern data center networks, actually, longer links and optics for those links drives the cost. They are more expensive than switch ports they are plugged in. So we really would like to use fewer links and fewer transceivers to build the network of the same size. Another driver is we want to reduce diameter and latency, at least for shortest paths, because non-minimal paths are still going to be longer, but for minimal paths, it would be nice to have 1 or 2 hops less. And there's a lot of research in HPC community and purely academic ones, and there are a lot of interesting topologies. Something new appears every year. Common property of those topologies is that all of them require some kind of non-minimal routing because most of their capacity is on non-minimal paths. Yeah, next slide. And just on the previous slide, I have a link to some nice talk which also describes some history of interconnects and also reasons why we are interested in new topology. Next slide, please, because I already summarized this. And let's talk about Dragonfly and Dragonfly Plus. In short, Dragonfly is a hierarchical topology. It has groups. There can be arbitrary topology inside groups. Original Dragonfly uses full mesh and also mentioned collapsed butterfly. And between groups, it's full mesh. But so groups essentially, when we are looking on intergroup topology, each group works kind of like virtual router with very high radix. And when we are looking inside the group, different kind of intragroup topologies, they can produce sort of different flavors of Dragonfly. And we are, yeah, that's the picture from our original paper, how Dragonfly looks like. And next slide, please. Yeah, and here you can see that Dragonfly can actually be smaller or larger. It can have very dense intergroup links, or it can be quite sparse. And sparse Dragonfly scales to very large numbers because essentially we have group, a lot of routers in the group, and only one link comes to any other group. That means number of groups could be very large, but it's kind of sparse connectivity between groups. Or we can build something dense. And dense Dragonflies are a little bit easier to work with, but they don't scale to such large numbers. Next slide, please. Oops, apparently expert to PDF doesn't skip some slides. Next slide, please. And of all the possible flavors of Dragonfly, we are interested mostly, and what I'm going to talk about next, in Dragonfly Plus, or it also was called Megafly in another paper. And essentially, it uses leaf spine, classical leaf spine topology for intragroup. Each group is a classical leaf spine blocks. And it scales well, and it has some very nice properties because essentially routing inside the group is a solved problem. We know how to do it with IP routing, and it's very nice. So we only have to figure out something for intergroup routing. For intergroup, we have solution. And I also have links to original papers and some presentation which discuss properties of those topologies. Next, please. Once again, sparse and dense, and as it applicable to Dragonfly Plus, if we want to build the maximum possible size network, we build it sparse for intergroup topology. It's enough to have only one link from a particular group to any other group. If we build more links between each pair of groups, intergroup connectivity becomes denser, but maximum possible size reduces. And very dense or compact Dragonfly is when not there is one or more links between each group, but when each spine in each group has link to at least one spine in every other group. And there's some terminology. Essentially, what we have, like we have intragroup connectivity, and there are local links inside groups. Links between groups are usually called global links in Dragonfly papers, and we can describe any path as a sort of signature of that path, indicating what kind of links packets going to traverse when it's going along that path. And so when we are forwarding packets inside the group, it's going to be something like LL. I mean, local links. When we are going through shortest paths between groups, we are doing local link, global link, and yet another local link in remote group. And then we can use non-minimal paths, and it's going to be something like local, global, local when we are going through intermediate group, and there is also possible to enter and exit intermediate groups through different spines, and in this case we are using a couple of local links in that intermediate group. Next slide, please. So, like minimal viable dense and sparse dragonflies, you cannot build that with few nodes. How they look like? On the left it's dense, on the right it's sparse. And dense is when every spine in every group is connected to every other group. That means to some spine is every other group. Next slide, please. And it's also just for visualization and for reasoning about Dragonfly topologies. It's useful to introduce the concept of planes when we just group corresponding spines in each group and call it a plane. It's not necessarily have full mesh connectivity inside each plane. It could be if it's dense. It could be less than full mesh if it's sparse. But anyway, it's kind of useful for visualizations. Next slide, please. So yeah, with few more nodes, it's going to be to look like this. Next slide, please. Or if we are trying to do that like on planar picture, it's going to be something like this. Next slide. The same topology as on previous slide, but with 3D and planes. Next slide, please. Next slide. And what kind of route path we have in Dragonfly Plus, and what kind of routing we need for that? Next slide. So just a note that simplified view of routing is that we care about connectivity. It's not true, because in reality we care about both connectivity and capacity. It's not very useful to have some very nice short path with not enough bandwidth. It's better to have maybe something a bit longer but with more capacity. And to achieve that capacity, we are using a number of tricks, at least in data center networks. Usually we exploit symmetry. So we pretend that all the paths are the same and we can group them. That means doing eCMP or maybe even weighted CMP. But underlying of those tricks are a lot of assumptions about symmetry in the network. Other option is stop pretending and try to explicitly deal with many paths, and those paths may be not equal, but some of them could be better, some of them could be longer, but still like try to deal more or less explicitly with them. And it's it opens a lot of options, but it's much more difficult to implement. On the other hand, problems with alignment symmetry is that in real world, symmetry is not going to stay perfect for long, because there are going to be failures. Many interesting topology, basically anything beyond multi-stage claw is less symmetric, and a lot of capacity is along non-minimal paths. We have to deal with them. And also, when we are relying on symmetry, we are using some sort of static traffic allocation schemes, and they could be suboptimal. So it would be nice to have a way to deal with imperfect symmetry, non-minimal paths, and maybe even some sort of dynamic traffic placement. And it's not restricted to Dragonflies, actually. Dragonfly is that the next thing after multi-stage clause, which is feasible to implement even with the tools we have. Next slide. So how routing looks in original Dragonfly, it's basically 3 hops, but those hops are what interconnection network people calling hops. So each hop can include, it's like virtual channels, it can include several physical links. And one hop is local inside the group, then another hop is global between groups, yet another is once again local in destination group. And that global hop between groups, it can actually go through intermediate groups. So it's a simplified view of routing in Dragonfly, but actual paths, when we consider physical links, they are going to be a little bit more complex. Next, please. And once again, from this point on, we are talking about routing in particular a flavor of Dragonfly Plus, a leaf spine inside the group. So intergroup routing, fortunately, is a solved problem. We know how to do that. And we are going to talk about what to do for intergroup, because it's the same intergroup topology as in original Dragonfly. We have non-minimal paths, and we need to be able to at least variant load balancing or better adaptive routing. Next. The same picture, dense and sparse, and let's see what kind of paths are available. Can you go back a slide? Because, yeah, I'm not sure how visible it is, but anyway, green ones. Yeah, next. Yeah, so by green, here we highlight shortest paths, and we can see that in dense topologies there are several shortest paths. Actually, the shortest path going through every spine in source group. But in sparse Dragonfly Plus, in this particular topology, there's only one minimal path. Generally, it could be more, but the point is that of all the capacity, a very small percentage of this capacity is available through minimal paths. Next slide, please. And this is essentially what minimal paths in Dragonfly Plus with 9 groups, 4 spines, and 4 planes. You can see that basically there is minimal paths going through every spine and every plane in dense Dragonfly Plus. Next, please. Let's talk about non-minimal paths. Here we have paths which go through intermediate groups. For this type of path, we need at least variant load balancing. And once again, we can see that in dense Dragonfly Plus, there are local, global, local types of paths going through each of spines, and there are many of them. In sparse Dragonfly, in this particular case, it's one, but once again, there are going to be local, global, local paths in sparse Dragonfly, but not much capacity is available via those paths. Next slide, please. Once again, this is 3D picture with local, global paths. You can just see that this path goes from the group through all the spines, and then they have to go through every accessible intermediate group. Next slide, please. And now we go to the most complex type of path. It's local, global, local, global, local. That means we go outside the group, go to some intermediate group, enter it through one spine, but that spine doesn't have direct connection to the destination group we're interested in, so we have to reflect through leaves in that group and go out through a different spine. And in sparse Dragonfly, like most of the capacity is available through these types of paths. Next slide, please. Once again, how those paths looks like, but this particular picture is probably not very clear. Anyway, what are the properties of those paths? Minimal paths are nothing interesting there. We know how to deal with them. Local, global, local paths of length minimal path 1. They have nice properties that distance to the destination at least don't increase along the path. And there is one hope where distance just stay constant. Minimal path 3 paths are more complex because at some point we have to actually go through the hope where the distance to the destination increases, and it makes life more difficult. Next slide, please. Next. So let's try to figure out what we can do with the tools we have right now in IP. And solution is that inside the group we can do minimal routing with ECMP because it's leaf spine, okay. But we kind of need to do variant load balancing, we are going from inside the group to other groups. Let's try to do that with VRF, and if we can do some tricks with imports and route leaking and install next hops from another VRF, probably it's going to work. That means that when going from inside the group to remote group, we are trying to use next hop for global links and install all of them. So even one of them represent minimal path, and so all of the others represent a longer path. We can try to install them so that forwarding state will be available to do just eCMP all those paths. And actually, on recent SIGCOMM, Google mentioned very similar implementation. They actually describe it very Dragonfly-like topology, but with some additional tricks like capacity engineering. Not going to go into the detail, but anyway, interesting paper. If you have time, take a look. Next slide, please. So that's how it looks like. That's our forwarding state we're trying to implement. When going outside the group, we are doing eCMP across all the available directly to the destination group and also across all the available intermediate groups. Next slide. And here, how forwarding state looks for inside the network core. Essentially, core is VRFs and links corresponding to intergroup connectivity. Next slide, please. So we figured out what to do with forwarding state. Then we'll talk about how to propagate reachability information to be able to build that forwarding state. And the side note that it's actually possible to do on like previous IETF, I thought that it's probably not going to work with just VRFs to trying to implement local, global, local paths, those of minimal path 3 lengths, but actually it's possible to do them. We need additional VRF in each group, which serves as kind of virtual link. And there are going to be additional import-export rules and so on, but yes, it's possible to do that. It's just more complicated than dealing with just minimal path 1 pass. Next slide, please.
You're running out of time.
Oh, I'm close to the end. So what we are trying to do for propagating reachability information, we are using BGP. Why? Because BGP is flexible, and with policies and communities, we can implement additional logic not available in the base protocol. So what we are doing is we are using communities, policies, and implementing like counting schemes, which limits how far and where our announcers are going to propagate. And when importing routes from the core VRF inside each group, we are doing some rewrite or path prependence, so minimal path and minimal path 1 path look equal, and that's it. Next slide. Next slide, because it's probably going to be talk for us next IETF. And next slide, please. I'm not going to go into the details, but basically, when we have paths of different lengths, they're definitely not equal. We can try to make them look equal, but they're not. And what we either want to fill shortest path first, then minimal path 1 path, and only then go to minimal path 3 paths. Now static traffic allocation scheme is going to do that. So we ideally would want to have some sort of dynamic adaptive routing. Unfortunately, it's kind of difficult to implement with IP. It's thing traditionally available in HPC interconnect. In IP, we don't have that, but it's possible to do something with tools available in IP. Basically, what we have ECN and transport-dependent feedback for congestion indication. And we have entropy headers, so we can try to influence traffic placement. And I'm really going to explore that topic and probably talk with congestion control people. preliminary indication is that it's possible to do something not as good as what we have in HPC interconnects, but at least something which works. Thanks. Yeah, and just to summarize, there is an initial version on draft, but it looks like my experiment with using Markdown for draft wasn't very successful, and Markdown converter 8 formatting and some parts of text. I'm going to upload the next version in proper way in XML. And I have some tools to generate topology, to visualize topology, and also to make some toy topologies with FRR and Docker, and I'm going to put that on GitHub. So for the next IETF, we probably will have something more material to discuss.
Thank you.
Thanks.
Linda, please, very quick question.
Linda Dunbar, I have a very quick question. So looks like the Dragonfly is really just eliminate the gateway. So you have your spine routers all interconnected together. Is that correct?
Yes, actually, it's kind of, if we had multi-stage claw and instead of dedicated top of fabric spines, we will try to use remote spines to reflect traffic. We would have Dragonfly Plus. So yes, we are trying to eliminate one of the stages.
Okay, so I remember at the beginning of your talk, you're saying that you try to reduce number of ports and links because they are expensive, right? So it looks like your Dragonfly topology actually use more links and ports because you have to connect to many spine.
Actually, now for comparable size, Dragonfly is going to use only 1/2 of long links. Because in multi-stage claw, we would have from spine level, link from spine level 1 to spine level 2, then back to spine level 1 in another group, so 2 links. In equivalent Dragonfly, we would have just 1 link from spine level 1, only level 1, no other spines, in one group to spine in another group. But there are limitations because on random traffic patterns, Dragonfly is more or less equivalent to multi-stage claw. For adversarial traffic patterns, it's only going to have half the capacity.
Okay, thank you.
Okay.
And last question, Tony.
Hi, Tony Lee Juniper. The magic words you're looking for routing are traffic engineering.
Thanks, I know. Yeah, source-based routing works very well. Unfortunately, a lot of state.
Thanks, and we are going to cut. So the current intention of this work is pure informational. There's definitely industry interest for different than cloud topologies. So we wanted to bring problem statement, explain how things work. At this point in time, we have nothing normative. So again, it's for this room that's full of people who are routing expert to look at the problem space and see how it can be solved in more innovative ways. Thank you.
Thanks.
So we are going to do the next presentation. So for people in the room, please make sure you sign in by scanning the QR code over there. That we don't get a room too small next time.
Okay. Hello, everyone. Thanks for chairpersons for accommodating our request to present the draft online at the RTG working group. In this presentation, we will introduce our work about routing framework for LU mega constellation based on region division. Due to the repeated development of satellite technology, widespread attention of satellite network, and broad market of satellite internet, the satellite network is on the fast track. The development of satellite networks has the following trends in recent years. First, for evolving from GU to LU or VLU, more satellites are needed to complete global coverage. Second, For evolving from point pipe to networked satellites, links between neighboring satellites become more frequent. Last, for evolving from ground to satellite links to inter-satellite links, the route selection becomes more complex. Routing is a fundamental issue in the satellite network, but above trends have following impacts on the inter-satellite routing, including sharply increased network management cost, massively increased routing message flooding, and dramatically increased routing computation. For traditional terrestrial network routing protocol, such as the OSPF-SS, the area division are used for the routing and management issues in large-scale networks. However, due to highly dynamic nature of satellite networks, the existing area division is hard to apply. As for existing improved terrestrial network routing protocol, based on orbit parameters, link state and metrics are predicted periodically to support route selection in dynamic networks. However, more frequent link changes in LU mega constellation cause a lot of routing computation. So, the current routing methods are hard to be applicable in future large-scale LU satellite networks. Considering these problems, we propose a routing framework based on region division to achieve efficient routing in the LU mega constellation. The details of this framework are as follows. Firstly, based on the connection relationship between satellites, the region planning is proposed to achieve adjacency relationship between regions. Then, based on the relative positivity between satellites, the new load type and capability are defined to realize flexible region division. Finally, based on the predictable topology in the satellite network, the inter-region and intra-region paths are constructed. The division of network region is pre-planned by the controller of the network through specified parameters. Each satellite usually has a fixed number of links which communicates with neighboring nodes. In a singular satellite constellation, each satellite may have 4 types of neighboring satellites, and each type refers to a direction. If the satellite contains a single antenna in each direction, the satellite usually have connection with 2 satellites in the same orbit and 2 satellites in different adjacent orbits, as shown in above figures. So, the quadrangle is adopted as a basic model of region division. In this way, satellites in each region and the adjacency relationship between regions could remain unchanged with the dynamic satellite topology. Each node is marked as XY. As shown in above figure, the satellite addressing would contain this information. Based on above parameters, the mapping function, each satellite could calculate the identification of the region where any satellite is located. In order to realize the region division, the corresponding capability of the satellite load could be classified into 3 types. Namely the internal load, the border load, and the virtual load. The internal load is responsible for maintaining intra-region network information, cross-region connection relationship, and inter-region network topology. The border load not only has the same function as the internal load, but also serves to establish and maintain connections with cross-region neighboring nodes and isolate network information advertisements between different regions. The virtual node is in charge of handling the network information and the topology change from the external network and presenting the time-varying geographical location of a region. Through above load capability, each node periodically calculates inter-region topology relationship, intra-region topology relationship, and the mapping relationship. Combined with above relationship, the intra-region routing table and the inter-region routing table could be achieved. The path calculation of each node is as follows. Firstly, based on the inter-region topology relationship, the inter-region path from the region where the node is located to other regions is calculated. Then, according to the mapping relationship and the intra-region topology relationship, the intra-region path and the path to the next hop region is calculated. If the destination node is identified in the local region, the intra-region routing table is used. The intra-region routing table is same as the terrestrial network routing. If the destination node is identified in the remote region, the inter-region routing table is used. The inter-region routing table is presented as follows, which replaces the destination address and the network mask with the destination region and aids the next hop forwarding region. There, we provide an example of the data forwarding. The satellite network is divided into 8 regions. At a certain time, the source satellite is located at region 2, and the destination satellite is located at region 5. The path between the source satellite and the destination satellite pass through region 2, 3, 6, and 5 in turning. As shown in figure, when the data arrives at satellite 11, following steps are executed. First, satellite 11 resolves the destination satellite identifier from the destination address and determines the region number of destination satellite as 5 according to the mapping function. Then, for the destination satellite and the satellite 11 are in the different regions, the satellite 11 queries the inter-region routing table, forwards to region 6, where the next hop node, satellite 3. Each node would repeat the above operations and finally forward the data to destination satellite. After region division, the path calculation between different nodes is divided into 2 parts. The path between nodes in local regions and the path between different regions. Therefore, compared to simply using nodes as a basic unit to calculate the path between different nodes, the computation with region division is reduced. There, we're taking Digesture algorithm as an example. We compared the time complexity of path calculation with or without region division. It can be seen from the above table that the time complexity of path calculation is significantly reduced after region division. However, due to no longer simply using nodes as a basic unit to calculate the path between different nodes, there is a certain degree of degradation in the path calculation, not a global optimum. So the path calculation results with region division should be verified. From the path calculation results between Sidley and Wuhan, it can be seen that there is no significantly degradation without region division. So the proposed routing framework based on region division could effectively address routing challenges in current satellite networks. In this year, my team has made a contribution for the satellite network in IETF, including use cases, routing issues, and emulation system architecture. In the future, we will continue our work in this field, including the extension of current routing protocol, the improvement of the routing algorithm, and so on.
Thank you. Tony?
Thanks.
Hi, Tony
That's all.
Lee, Juniper. So first question, I've got two questions. First question, it seems like your routing regions correspond exactly to an IGP area. What did you consider looking at just using the IGP in a hierarchical mode?
Yes, at present, the proposed routing framework is mainly aimed at the improvement of the existing IGP to adapt to the LU mega constellation. Thank you for your question.
What was the problem with using routing as it is?
I think the terrestrial network generally adopts the manner of the area division to improve the efficiency of routing convergency and network management. But the existing area division method typically divide a network into a backbone area and multiple low backbone area. The backbone area is unique and has routing information of all areas. The low backbone area establish fixed connections around the backbone area. Those nodes in the backbone area are responsible for traffic forwarding between all areas and require higher performance. However, the performance of satellites normally is peer-to-peer and limited, especially in singular layer satellite constellation. The current area division method could easily make the backbone area congested in the satellite network. Besides, due to the dynamic satellite network topology, the connection relationship between different areas is unable to maintain stability, and each area needs to exchange routing information continuously. So, in our work, we think the existing area division method is not only inefficient, but also less flexible and can't meet the requirement of routing in the satellite network. So we make some improvements.
Okay, well, I think you should take a look at ISIS. It does not have a requirement for a backbone area. I think you might have a little more flexibility there. Second question, I know nothing about orbital mechanics, but my understanding is that there are situations where the orbits are not synchronized and the members of satellite connectivity between orbits is not constant. Does your solution address that issue at all?
Thanks for your question. For this problem, I think the satellite, the location of satellite in the constellation, the relative location is static. So we can addressing the satellite address and contain this mark. Thanks for your question.
Okay, third point, I'm co-chair of the TVR working group. I'll put my working chair hat on and say that this might really actually fall under our charter.
Andrew Alston here, routing AD. I am not sure if this fits into TVR or not, and it's a kind of was my gut reaction as well. What I would say at the very least is I think that this should probably be presented in TVR to get some thoughts and feedback out of the working group to ensure that if TVR does believe that that is where it belongs, you know, let them say so. But I do think that this should probably be taken to TVR at the very least for comment.
Just jumping in here, it's Jim Guichard, routing AD as well. To follow on from what Andrew was saying, the other working group that I think this possibly could fit into is MANE. So I think at the very least there should be a conversation with you know, TVR and MANE to take a look at this work to see if it is something that would fit into those charters, and so let's plan to do that.
Absolutely.
Okay, Jeffrey from Juniper. To add to what Tony was saying earlier about ISIS does not have a backbone. Even in OSPF case, that backbone can also have virtual links through non-backbone areas, and those virtual links can also be dynamically established. So similar mechanism does exist in OSPF as well.
Hi, Rashmida Kavin from Huawei. One of the problems that probably the mechanism that you're introducing is forgetting that the satellites actually move against each other, especially around the seam, and especially when you go to constellations like Walker Delta with the fifth link. This notion of seams is everywhere. So any type of configuration of areas and levels and things like that will break the mechanism of the traditional OSIS or OSPF configurations and will result in route failure. It's not a simple Manhattan grid. It's a constellation that actually with a whole bunch of nodes moving against each other. As long as you stay within one plane, your probably scheme will work. But as long as we are going to do inter-seam type of routing, this system of configuring or dynamically configuring the areas and levels will break. So you might want to consider that. The other comment that I wanted to have is that aside from inter-satellite routing, the optimum goal of the satellites are to route to the ground. So some sort of addressing has to be managed in terms of what satellite, for example, at any given point in time is covering what type of nodes on the ground, and take that into consideration when we are routing. So two type of routing. One is between the satellites that we probably will use for the OEM type of things, and the other one for the actual data path that will end up on the Earth. There are two different systems that we need to consider. The third comment is that I actually agree with Tony. We need to actually ratify these things with within the TVR and see whether or at least take a look at it before actually bringing it to the routing systems. Thank you.
Thanks.
Ling Han from Future Way. Two questions. Have you considered the link state changes for horizontal link when the satellite move to a polar area? Because all horizontal links will be swapping when they move to polar area in about 90 minutes. That's a very dynamic state changes. I don't think current routing protocol can handle that. Second is that all satellites may have the ground station connection, and the number of those links is huge. For Starlink, they will support 1 million users, which means it's millions of the UE to satellite link. How can you handle this network with those state changes with this technology? Thank you.
Hi, Rashman again here. Yes, thanks for your comment.
Are you answering on behalf of the authors?
No, I'm just commenting on what he just said on the previous comment. It's true that the satellites actually, when they approach the pole, the links go down and actually they reverse the nodes. So the same situation that I was talking about at the seam and at the Walker Delta with the fifth link sort of exists around the pole. So that's very valid comment that we need to consider. And I don't know how this scheme actually is going to actually work when it comes to that type of work.
Thanks. So we'll take it to the list, and sorry, we are going to cut here. We are going to talk to managers as well as to talk and consult with Tony and co-chair to see where it goes.
Thanks. Trying to make up for the time. This is the problem statement for Rosa. Rosa had been presented in 2 previous IETFs, and I asked for a brief slot today to give an update to the larger group. What has happened since, to give you a quick rundown, you may have seen this on the list. We established a non-working group list called rosa@ietf.org, which you can use for discussion. Thanks for Jim sponsoring this. We separated the original draft that was presented in 115 and 116 into 3 different drafts, cutting the large document down into the more typical structure of problem statement and use cases, gap analysis and requirements, and an architectural draft. Today, I just wanted to briefly outline to you the problem statement part. So I'm not going to go to the 3 of them, just the part on the problem statement. I hope this works. Yes. So and we presented this yesterday in a side meeting, to which I will talk a little bit at the end. So service routing, as it's done today, you can see on the right-hand side, usually explicitly resolves the service name, foo.com or anything similar, onto a network locator. You use an indirection infrastructure to do that. The client issues the request first, and you then utilize the result in order to talk in the actual application level request to the IP address. So very schematically outlined on the right-hand side. The example technologies that we're looking at in the gap analysis draft are things like the traditional DNS and with its particular improvements in order to load balancing and CDNs. Alto is another one we're talking about, HTTP redirect. Lisp, to some extent, in Lisp, the client doesn't actually do the resolution. It's done by the ITR, but we have them in the gap analysis as well. And we describe a number of use cases in the draft that you're free to read. I think in the end we grew to 11, if I counted correctly. So quite a number of use cases. And these are the issues that we describe across the use cases. Then they don't apply to all of the use cases throughout, but in total, these are the issues we observed. The one thing is, we're interested in any cast type of problem. So you have more than one service instance, meaning more than one choice available. You need to make a choice where to send your request. That's common across all the use cases, really. The decisions are usually dynamic, which means you may want to change the choice where you actually send your transaction to frequently. And in some of the use cases, that's rather frequently, even down to single requests. In particular, if you have stateless requests, like retrieving files or chunks from replicas, you can send that request to any of the replica, really, in order to be retrieved. And in some others, the dynamicity is slightly slower. We also have, in some of the use cases, aspects of what we call ephemeral service instances. So if you use architectures like microservice architectures, service instances may appear or disappear rather quickly. And rather quickly, there really means if you look at serverless infrastructures in less than a second or even less, you may deploy or ramp down an instance in a network location. Latency is an issue that occurs across all the use cases. You have an explicit resolution that takes time. And in some of the use cases, we specify those or we quantify that time based on various measurements that are available. And in some of the use cases, ARVR is one of the examples that we have in the use case draft. You possibly exceed the delay budget when you do that. You don't have an awful lot of time, so spending 15 to 45 milliseconds to do a DNS resolution is not a very good time. So obviously, you want to do that maybe at the beginning of your overall service, but that then goes counter the potential desire to change the endpoint rather frequently, because then you have to repeat that latency, that resolution again. Selections may be service specific. So what fits for one may not fit to another. So we outline in some use cases service specific policies to actually make the anycast decisions. You need to accommodate those. They may not be the same across various services. The deployments are distributed. So this is a problem where service instances may exist in a number of network locations. We are not really interested in instances being managed by a service platform, like for instance, Kubernetes in a single data center. That's the problem of the service platforms. But if it occurs across different network locations, you have a routing problem, really. That's the point there. Namespace mapping, not everybody uses URLs. That may be surprising, but we found that in some of the use cases, we make reference to the quicker draft, for instance, from Colin Jennings, who uses a application ID scheme, which are 128 bits as a shorter representation of very, very long URLs. And service chaining is another aspect. So the question that we're asking in the problem statement is, what if we had a similar end-to-end procedure, which is meaning it's initiated by the client, very similar to the DNS, of data communication between the client and what is a best choice of service instance out of a set of possibly many service instances. But that procedure would significantly reduce the latency instead of having the latency through an explicit resolution. And it also allows potentially for updating the assignments of the service instances rather frequently, at least at the rates that are more aligned with the possibility to establish new service instances. If I can establish a service instance in a second or less, it would be nice if I can actually use that new service instance within a similar time frame. That's not necessarily the case if you use, for instance, DNS, where updates may take a very long time to propagate. So what are some of the problems you need to address when you ask that question? The first thing is, how do I even make decisions on these anycast-based assignments at a relatively high rate? As I said, even down to a single service request, so that I can have scenarios like we described for the AIVR or the over-the-top video chunk retrieval, where one request is sent to one choice, the next request is sent to another replica. How can I do that? In particular, how can I do this without the need for an explicit out-of-band discovery? If I do that discovery, it will cost me the latency, which again may be an issue. How could we improve on the update speed? Does it really need to take minutes or longer to update the mappings, the assignments between the service name and the best IP locator, so that I can go down to that rate of service instances being established? How could we incorporate service-specific policies to address one of the issues we mentioned before? How can we support individual, or actually any application identifier, so not being limited to URLs only? Chaining is another question. How could we do chaining without an explicit discovery latency that occurs? And last but not least is the client-driven operation. How can we avoid through a client-driven operation that we have any transaction state in the network? You can see this in some of the solutions we looked at in the gap analysis, but there is the possibility to create transaction state in the network, and that may not be desirable for a number of reasons. Some words on the side meeting yesterday. Again, this is a problem statement that we presented yesterday. We created this side meeting, we announced it to this list as well as to the larger group, and then also on the individual smaller list. The material and the agenda, the slides, and since about 10 minutes, you can also see the notes from the meeting, which my colleague Antoine gathered together, is on this public GitHub. You can download and view the material yourself. If you haven't made it to the actual meeting, we presented, apart from the use cases, we had more use case slides. You just saw the problem statement, which was the shortened versions of the slides you see there. We presented two use cases, the web browsing and content delivery. The actual problem statement, which you've just seen, gaps in existing technologies. We covered DNS, CATS, because that was a question from the last meeting in London, Alto, Lisp, and we also have some relations to what we call related technologies. So not necessarily technologies that realize the problem, but maybe of interest to us. And we also had discussions and a presentation on a possible blueprint. Now, the blueprint there was a balance between outlining architectural concepts and also giving hints on how you could implement that. The reason for doing that is because we didn't want to stay in the conceptual place only. We have found a way of doing it, and we also recognize that's not the only way of doing it, which then gives us the ability to at least have a stake in the ground to talk about. But also, we made clear yesterday that that's not the starting point to say we have a solution. We have a way of doing it, and we recognize the other ways of doing it, which is exactly the discussion we want to have. We had quite a bit of discussion yesterday, also thanks to Dino on, is Lisp a potential way of doing it, which it is. That was part of our initial or internal consideration as well. And it's quite interesting to see how we could actually utilize Lisp for addressing some of those problems. We discussed in general the validity of the problem, and I think there was some understanding for that problem and a recognition the problem does exist. In particular, in the use cases we presented, we also made clear that there is a huge range of use cases and huge range of users of the internet where that problem doesn't exist. And I think I tried to make this clear in London already. This is not a replacement of the DNS. The DNS works perfectly well for most of your applications that we're using every day, but there are applications in which that latency matters. And for those, that problem does exist. So that's the discussion we had yesterday, and I think we reached an agreement on that. And we're now in the discussions on possible ways forward. The discussion on technology is trying to see where we can fit this either in existing work. If we don't find a good place in existing work, do we want to create work? That always sounds terrible, so it's probably preferable to find ways to do this in existing efforts. So there will be added verbally. This is just what I did now. Please look through the notes in case you made it to the site meeting. If you haven't made it, send questions and comments on this either to the list or to the individual co-authors, Louis, Jens, Paolo, or myself, and we will help you how to go forward. We hope that in the next IETF we can have more discussions on what we decided as a group to go forward. We will keep the routing working group list updated in a loose form because we have now an own mailing list, which we obviously want to use as a focus of the discussions. And on the last, oops, does that? Yeah, it does go. If you have somehow find a linkage in your mind to what I briefly presented here, please join the discussion on the mailing list. It is growing, but we'd like to see more people there. And we'd like to see contributors. If this is a problem for some of the use cases you are considering, please talk to us. We can either add use cases. We still have a couple of use cases in mind ourselves, but love to hear use cases from other people as well. If you feel that there is a technology we are overlooking that may address, happy to extend the gap analysis. And if you even know how to solve it, brilliant. We have a probably growing work on technologies that we'd like to do. And hopefully we'll be back in Prague with telling you about new ways. How that will look, we will decide until then. Thank you. Any comments, questions, criticism?
Jeffrey from Juniper. How does this relate to cats? Because a big problem of the cats is for the ingress router to figure out which routing instance to use and then how to get traffic there. So that seems to be related.
So the gap analysis draft outlines that in more detail than probably I will have time to say. So cats is one of the, because it was mentioned the last time, it's one of the aspects that we have a closer look at. The one thing is, of course, cats has two orthogonal things that it looks at. It's the computer awareness part. Now, we don't care about computer awareness specifically. We have some use cases where computer awareness is one of the drivers, but not all of them. Or I would say the majority are not particularly computer aware. And the other part is the TS part, the traffic steering, which is what you mentioned. And that is something where we feel there's still a different angle to how this starts. CATS is more an in-network decision mechanism to make traffic steering decisions within the actual ingress nodes, which is not the starting point where we started. We started with the way the DNS works and where application developers usually make a decision through the resolution service. So it's a different starting point, and it addresses therefore also much potentially wider scenarios that are not necessarily compute aware centric. More details we have in the part. They're also technology aspects. So at least, and that's a bit difficult, of course, to judge at the moment because CATS is fairly young. But you can, of course, see technology work emerging, and we have more comments in the draft to that, to the differences. But that's a little bit premature because CATS is fairly new. So we also don't want to presume CATS going in a certain direction and then later be accused that they're kind of like fixing that direction. We're not doing that. We just look at what's currently out there, and we are observing the differences.
Okay, I'll read more on this.
Thank you. Okay, thank you very much.
Thank you.
Leo.
Hi, chairs. Can you hear me?
Yep, please try to talk louder.
Okay. Is it any better?
Very good.
Okay, perfect. Shall I go ahead or?
Please go ahead. Introduce yourself and why you're here.
All right. So thanks a lot, Jeff and Ingen. So this is Nicola from the Scion project, and I would like to give you today an update about Scion, and specifically to present the control plane. I'm here together with my colleague Karim, who will take over at half of the presentation. So in case you have wondering what Scion is and you have not heard about it before, Scion is a path-aware internet architecture that started a few years ago in research, and it focuses on three fundamental properties: availability, not only in case of failures, but also in presence of adversaries; security, especially when it comes to the routing part; and scalability. And over time, it kind of slipped out of the lab. So today it is in production use by a few ISPs in Switzerland. It now powers part of the Swiss interbanking network. There's even multiple implementations. And that is why I think for the project, it is really important to get a clear specification. So if you're wondering more about, for example, the motivation, and if you want to get an overview about Scion, I can recommend you to have a look at the overview draft. Scion itself is actually composed of a few components, and that's why, to clarify that, we also wrote a component analysis draft that tries to clarify what each component is doing, what the inputs, outputs are, and how they relate between each other. So last time that we presented Scion at this working group, we briefly presented the PKI. That was back at 115 in London. And today, actually, we have a new draft that presents another component, the control plane, which is actually the one doing the routing. So I hope this will be of interest of this working group. So before we get into the details of the routing part, I wanted to quickly introduce some fundamental concepts and introduce the three main components. So on the right side, you see an example topology, and in this topology, there's 19 autonomous systems, the little nodes here, and these ISs are grouped into what we call isolation domains. And isolation domains offer isolated routing planes, and each ISD has its own root of trust. And within each isolation domain, there are some ASs that have some special functions. They are the so-called core ASs that you see circled in gray on top. And later on, we will clarify their role. So Scion is an architecture that is based on path segments and endpoint path control. So the data plane is fetching these segments and combines them into end-to-end paths that in the end are used to send traffic to any destination. And this endpoint path control is actually enabled by including the desired forwarding path directly into the Scion packet header. So here you see a very high level example. And that means that Scion routers are relatively simple. They just look at the next hop in the packet already, and then they can forward packets also statelessly. These paths have to be provided by something, and that's where the control plane, the routing part of Scion, kicks in. So the control plane is actually discovering path information, and then it disseminates it down to the endpoints. This information is also authenticated. And it is important to remember that routing is based on this ISD-AS tuple as a routing locator. So this is somehow decoupled from end-host addressing that can reuse existing addressing schemes, for example, IPv6 or IPv4. And as this information is authenticated, that's why Scion has its own PKI. It provides its, let's say, unique trust model where each ISD has its own roots of trust. And it makes these certificates available to the other components. A few words about interoperability. You have seen that Scion packets are a little bit different, and that's why there are transition mechanisms like the Scion to IP gateways. These are not part of this draft. We briefly mentioned them in the overview draft. Besides that, Scion has no prefixes on Scion routers, so that's why transition mechanisms usually leverage RPKI for origin validation. And when it comes to routing, Scion is interdomain only. So that means that within an autonomous system, Scion is reusing the existing infrastructure, the existing routing protocol, and the existing forwarding. Scion only acts at the intradomain part. Ultimately, path selection is left to endpoints, so this can be potentially integrated with existing path selection mechanisms. I already see my colleague Corinne online, so I'm gonna hand over to her for a deeper look at the routing part.
Thank you, Nicola. Yes, I'm now going to explain the control plane routing process a little bit in more detail. Can you understand me? Is it okay?
Yeah, you sound good.
Okay, thanks. So the routing process in Scion consists of, say, three phases or stages or processes. First is about really discovering a valid path through what we call beaconing. This is the exploration phase, and there we discover passes between the cores of an isolation domain. This is called inter-ISD beaconing or core beaconing. And then the intra-ISD beaconing is the discovering of paths from the core to the child ASs. So this is downwards in a way. And then Scion ASs can select path segments and make them available to other ASs. This is called, or this happens in the registration phase. And each AS can freely choose the algorithm and the criteria based on which they select those path segments which they want to make available to other ASs. And the beaconing happens from the core to the down to the child ASs, but a path segment which is registered can also be used in the other direction, so up. And then in the end, this is done to be able to communicate from one source endpoint to another destination endpoint, and to use these path segments to create an end-to-end path, which is then, as Nicola already said, incorporated in the packet header. And this phase is called the resolution or the lookup and combination phase. In this lookup part, the ASs, the Scion ASs, look for path segments towards the destination AS, and this happens in the control plane. And then the actual combining of these path segments into an end-to-end path, it happens in a data plane. And the first processes, the exploration and the registration happens by the Scion control service, which each Scion AS has. And the endpoint is really responsible for the resolution. So I go with a little bit more in detail about the path exploration or the beaconing phase. This happens by core ASs. They periodically send so-called path construction beacons to start this exploration of paths. They are either sent to other core ASs, either within one isolation domain or also to another isolation domain. And the other way is to send these beacons top down from parent to child, which is then the intra-ISD beaconing. And each AS receives beacons and they put them in a beacon store. And per propagation period, which each AS can define themselves, each AS also selects a subset of these receives PCBs, again, according to their own needs and selection criteria. They append routing information to this PCB about the routing through this specific AS. They sign this routing information with a signature, and then they further propagate these selected PCBs to the neighboring ASs. So these PCBs, they accumulate cryptographically protected path and forwarding information on their way per traverse AS. And basically, one PCB contains first a timestamp of the moment it was initially sent by the core AS. There's also a mentioning of the expiration time, but because the PCB is not valid forever. It has an ID. It consists of a list of all ASs on the path which it has traversed so far. And yes, as I see, signed routing information per AS. So an AS, sign AS not only propagates PCBs, but it can also store or register selected PCBs as path segments. We have up path and down path segments. The up path segments, they are chosen by an AS and they represent how this AS wants to communicate with its core ASs, with the core of its isolation domain. And an AS stores these up path segments in its own local control servers. And the down path segments are how an AS wants to be reached by other ASs and other entities. And these segments are registered with the control services of the relevant core ASs in the core of their own ISD. And these up path segments and down path segments do not have to be the same by definition. And this all is done, this routing is done to, in the end, resolve an end-to-end path from source endpoint to a destination endpoint. And this path resolution has, as I already mentioned, two steps. First, a source endpoint looks up the path segments to the destination AS, which happens in the control plane. And then it combines this in an end-to-end path, which happens in the data plane. And this looking up requires, so looking up path segments requires the lookup of up to 3 path segments to be able to then in the end combine an complete end-to-end path. First, you need an up path segment to reach the core in your own source isolation domain, your own isolation domain. And this up path segment is delivered by the control servers of the source AS, so the control servers of the source endpoint. Then you may need a core path segment to connect the core of your isolation domain with the core which is connected to the destination AS. This other core AS can be located in the own ISD, but also in another isolation domain. And this core path segment is delivered by the control servers of the core AS in the own isolation domain. And in the end, you need a down path segment to be able to connect to the destination AS. And this is delivered by the core AS, the control servers of this core AS in the ISD of the destination, the endpoint AS. So you have to, and source endpoint has to request a couple of path segments. And to improve efficiency, it is recommended requesting these path segments in parallel. And then also, it is also a very good idea to cache the return path segments so that you, especially in case of very often used paths, you can just get them out of your own control service or path database. Then S-Sign is developed or designed with security in mind. There are also a couple of security measures which make this process in the control plane secure. First, as I already said, that PCBs are signed by each AS they traverse in an onion fashion way. That means that an AS does not only put a signature on its own contribution, the routing information about its own AS, but also puts a signature on all the other the routing information of all the other ASs. And then every AS should verify the routing messages, and they can do that by following the certificate chain. Then the specific routing information, the hop information of one AS, like the ingress and egress interfaces, they are also authenticated by means of a MAC, message authentication code. And this is checked by the routers during the forwarding of the packets. And each AS should only forward traffic on paths that are explicitly authorized. And then, as my colleague Nicola already explained, in SIGN we have the SIGN control plane PKI, which is scoped on isolation domain level. So the roots of trust are also only on this ISD level or scoped, and this makes it very almost impossible for low global kill switches to appear. This section is not available in the draft yet, which we have a control plane draft submitted to the data tracker. You see the link on the bottom of the slides, but this security consideration section is not there yet, but will come soon. And so in summary, SIGN is a future internet architecture which is already in use, and the control plane provides path-aware secure inter-domain routing. As I said, we already do have the draft available, but we should add the security consideration and also a YANA section. But you can already read the draft, and every feedback is very welcome. Thank you. So are there questions or comments or already now?
Thanks, Corinne. So, question to you. Having read all the documents, they are very hand-wavy about convergence times, and we care not only about security, reliability of internet, but also about how long does it take to converge, how long does it take for particular failures to be avoided. There's some text about use multipassing, hide the failures, but unfortunately, we can't always hide the failures. So more tangible data on actual convergence times, reaction of protocol to different failures would be very much appreciated. And IETF really cares about these parts of routing.
Yes, so it is our draft, so they are not in a final state yet, and we definitely will add more information. I think also my colleague Nicola wants to say something about this.
Yeah,
Nicola, would you want to add
I
something?
just wanted to chime in. SIGN does not really have a convergence time in the sense of like BGP, just because this routing is based on this beaconing, which is usually a kind of semi-directed flooding. But there is definitely quite some data and also experiments about that. So we are happy to add something like a section in the draft. So thank you.
Thank you. I don't see any questions.
Originally, we had some time for open discussion, but right now we only have 2 minutes left. So if anybody wants to say anything, right now is the time.
We're done for today.
If not, we'll see you on Friday.
Thanks, everyone. Yeah, but you cannot just leave. What's not the intention of it? No, I'm just using some example. Practically, we need to be open to new ideas and always compare new stuff with this.
Some more.
Yeah, so there is also. So just look something. There's a bunch of good, Italian. So, you will